Hi Math, I'm Andy. Today we're going to look at the idea of implicit differentiation. Now let's say we're given the equation of a circle, x squared plus y squared equals 9. And we're asked to find the second derivative with respect to x. And so if we're taking the derivative of a circle with respect to x, and we have this y squared in there, that's where we have to use this idea of implicit differentiation. So the first move that we're going to want to make is take the derivative of each of these terms with respect to x. So the derivative of x squared is 2x. The derivative of y squared is going to be 2y. And then we're going to have this dy dx kind of come out due to that implicit differentiation style. And the derivative of 9 is 0. So now that we have this dy dx, we want to solve for that dy dx. So what I'm going to do is subtract 2x on both sides just to get that dy dx term by itself. So I have 2y times dy dx is equal to negative 2x. And to get the dy dx by itself, I'm going to divide both sides by 2y and simplify. And so we found that the derivative dy dx is equal to negative x over y. So what this means is that given a circle with an origin, center, and a radius of 3, the derivative or the slope of the tangent line at any point on this circle has a value of negative x over y. So you tell me the point, I plug it in, and I can tell you the slope of that tangent line. But our question wants what is the second derivative of this circle. So we need to take the derivative of the derivative. Now we'll notice that this is a quotient, so we need to apply our quotient rule. Our quotient rule, ultimately, if you're taking the derivative of a function that is a quotient, the rule is the denominator times the derivative of the numerator minus the numerator, sorry, I'm running out of space, divided by the denominator squared. So we'll look up the quotient rule, but really it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And so we'll just show you what it is with ours. So again, it is the bottom, which in this case is y, times the derivative of the top, which is derivative of x is 1. There's this big negative. I'm factoring out that negative. Then we're going to have a minus the top, which is x, times the derivative of the bottom, which the derivative of y is dy dx, all divided by the bottom squared. So this is the derivative, and what we want to do is we want to get that dy dx, we want to get that out of there. So if we are taking the derivative of the derivative, well, what I notice is I actually have a replacement for it. So in my second derivative, I have this dy dx variable, and I have a value for dy dx. We say that it's negative x over y. So I can actually use substitution to replace this dy dx with a negative x over y. So writing this out kind of in a simplified form, my second derivative is equal to y minus x times negative xy over y squared. And I didn't forget about that negative that's floating, that negative that's still there. Now, this can also be simplified in calculus class, just like any other math class. We like to kind of break our answers down as small as we can. So this x and this x, well, this is going to become a plus because I have a minus minus. This is going to become x squared, so I have a y plus x squared over y squared. It's still a negative. Now, I'm going to simplify the numerator by having common denominators. So I have to multiply y over y here, so they both have a y. So I end up, instead of y, I'm going to call this y squared over y. So now they have common denominators. So I have this y squared plus x squared over y squared. And to simplify this further, this y kind of comes down in my denominator. Really what I'm doing is simplifying this by multiplying by y on top and bottom. That's going to cancel the denominator in the numerator. And so I have my second derivative is negative, that's still there, x squared plus y squared over y cubed. And so we found our second derivative by finding the derivative of the circle itself implicitly, solving for the dy dx, taking the derivative of the derivative, and then seeing that we had a substitution we could make just to keep everything in terms of x's and y's. Now, I just want to look at one last thing. I noticed that in my second derivative answer, there's this setup of x squared plus y squared. And when I look back at my original problem, I see that there is an x squared plus y squared equals 9. And so in my one last substitution swoop, I'm going to take this x squared plus y squared, I'm going to pull it out, and I'm going to replace it with the value that's equal to x squared plus y squared. And so I'd say that the second derivative of this circle is negative 9 over y squared.